Taking a look at number 6 here. Okay, number 6 tells us that the captain of the ship wants to go directly south across the river at 15 meters per second. Wants to go. Okay, is that where the captain of the ship is going? Yes. Is that going to be a solid line vector, or is that going to be a dotted line vector? The captain of the ship wants to go south. When I draw that 15 meters per second to the south, should I draw it like this, or should I draw it like this? First one or second one, Bailey? Second one. If the captain of the ship actually goes or wants to go directly south, we're going to make that a dotted line vector, a resultant vector, and we're going to label that as 15 meters per second. Now, there's a current in the river of 5 meters per second to the east. Clearly, that's got to be a solid line vector because we can only have one dotted line vector. But it makes sense that it should be solid as well, right? Solid line vectors contribute to where you actually go. The river current isn't where you go. The river current contributes to where you go. It has a part in where we actually end up going. So that is going to be a solid line vector, and it's going to be drawn like this, 5.0 meters per second. Now, where am I going to draw that? Where do I want to draw that as part of my vector diagram? We got to make sure that a dotted line vector is not drawn according to the normal rules of vector diagrams. Okay, most of the vectors go front to back. Okay, the resultant vector, the dotted line vector, doesn't do that. The resultant vector, or the dotted line vector, goes backwards. So we got to make sure that my solid line vector looks something like this, 5.0 meters per second, where it's head-to-head, or front-to-front. That allows me to draw my other vector, my other solid line vector, like this. Is that vector diagram drawn well? Sure. My solid line vectors are drawn front to back. My dotted line vector is drawn from start to finish. And that's exactly the way that it should be. We want to find the length of this green vector, the length of this solid line vector, in other words, where we have to aim, and we also want to find the direction here, the angle here. Now, this is different than our other questions in the sense that we're not looking for our dotted line vector. In all the questions that we've done to this point, we've had to solve for the dotted line vector, the resultant vector. Here we have it. But it's the same as the other questions in that we're still looking for the hypotenuse. So mathematically, it's no different. We're still looking for that hypotenuse given the adjacent and the opposite side. Let's say v is going to be equal to the square root of 15 squared plus 5 squared. Do the math on that, and it works out to be 16 meters per second. And let's say theta is equal to the inverse tan function of opposite over adjacent. That's going to be 5 over 15, which is going to give me 18 degrees. Now, the way that I have this drawn, this would be 18 degrees south of west or west of south. Which one is this going to be? Yep. It's going to be west of south, yes. Because you can see that my vector here, my green line vector, is drawn from the south. Okay, it's measured, the angle is measured from the south axis here. So it's west from south, or west of south. Or you can look at it as go south, then we go west to get to that point. Okay, south after west, or south up west. How many people got that one right? Right. So go to number 7. This one says the pilot of an airplane wants to go south at 130 meters per second. Solid or dotted line? You want to go in a certain direction, that's going to be it's as if you actually are going in a certain direction. It's going to be a dotted line. So let's draw that as a dotted line vector. 130 to the south. There's a wind blowing to the west at 20 meters per second, so we draw that to the west like this at 20 meters per second. Okay, we have to put those two vectors together, and then we have to figure out what direction we have to aim in order to go 130 meters per second to the south. Let's put these together here now. We're not going to draw it like this because that means my dotted line vector, my resultant vector, isn't drawn properly. It's got to be from start to finish, and clearly it's not going to the finish here, it's going to the start. So I'm not going to draw it there. The better option is to draw my 20 meters per second right here. Now, I'm going to draw my other solid line vector. That's where I have to aim. I'm going to draw it right there. so that my dotted line vector is still drawn from start to finish, and that my solid line vectors are drawn front to back. That works. Okay, logically it works as well. Not just mathematically, not just graphically, but logically it works as well. If you want to go south, but there's a wind to the west, where are you going to have to aim? South, east, right? You have to aim opposite to the direction of the wind. You know that if you're traveling down the highway and there's a wind blowing that way, really, really strong, your steering wheel kind of gets turned like this, the opposite way. You have to aim opposite to the wind to end up going straight. So as much as we didn't necessarily think about that as we were drawing the picture, okay, we can think about it after the fact and see if our picture is reasonable. And it is. Travis? Yeah, it is, because it's still the longest side. This is still 90 degrees right here. This is still the hypotenuse. It's just not the resultant vector. So mathematically, it's no different, because it's still the hypotenuse. It's just conceptually, we're solving for a different vector, not the resultant, but we're solving for the vector at which we're aiming. Okay? The green one there. All right, so let's do our thing here. Again, it's just mathematically exactly the same. V that we're looking for, 130 squared plus 20 squared. Do the math there, works out to be 1.3 times 10 to the 2. And solve for theta, which is always going to be drawn at the start of the diagram. Theta is equal to the inverse tan of opposite over adjacent, 20 over negative of 130. And that works out to be 8.7 degrees. 8.7 degrees south of east or east of south. We're not measuring it from the south, we're measuring the angle from the east. So it's going to be, sorry, we're not measuring it from the east, we're measuring it from the south. So it's going to be east of south, yes. 8.7 degrees east of south. Got it? Okay, I want to do one more example here, and that'll be the last example of this stuff that we do. And then we will assign the last couple questions and move on to the next topic. The next topic, which is our last topic of the unit. Last example, you have to copy down this unit too. So it says the captain of a ship travels directly west across the harbor at 24 meters per second. There's a current of 10 meters per second to the south. Where did the captain have to aim the ship? This captain goes directly west across the harbor at 24 meters per second. That's where he actually goes. Solid or dotted line? Dotted line, good. Where he actually goes, 24 meters per second to the west, is a dotted line vector. Now, whether that's going to be my hypotenuse or whatever, we don't know that yet. Okay, we've got to draw the rest of our vectors to figure that out. There's a current in the harbor of 10 meters per second to the south. It looks like this. Where am I going to draw that on my first, relative to my first vector here? Right here? Does that work? Those are drawn front to back. That's right, right? They're not supposed to be drawn front to back because I've got a dotted line vector there, a resultant vector. So I've got to draw that second vector right here. That's going to be 10 meters per second. What am I looking for? This one right here. Looking for V, looking for theta. Is this not the same thing? Okay, the diagram looks a little bit different, but again, mathematically, it's exactly the same thing. We're looking for the green vector where the captain must have aimed the ship, but it's still the hypotenuse, and we're still going to find it in exactly the same way. We're going to say V is equal to 10 squared plus 24 squared. Square root that. We're going to say theta is equal to the inverse tan of 10 over 24. We're going to get a number for both of those. We get 26 meters per second for the speed. And for the angle, we end up getting 23 degrees. What's that going to be? 23 degrees. It's north and it's west. Is it 23 degrees north of west or 23 degrees west of north? Which one is that, Nick? North of west or west of north? What does that look like? North of west, yeah. It's north of west because the angle is measured from the west, of the west. Okay, does that make sense? From the west, of the west. It's not measured, the angle is not measured from the north. Okay, it's measured from the west. So north of west. All right, I'm going to assign 2 more questions for you to work on for homework. You might have a little bit of opportunity to work on those later on today, for sure during scheduled help, if nothing else. Please, for homework tonight, work on questions 8 and 9 on your sheet. All right? 8 and 9 on your worksheet. Today we're going to start our last topic of the unit that we call projectile motion. We have to know what a projectile is, first of all. A projectile is an object that moves through the air, or through anything, I suppose, under the influence of just gravity. Nothing else. No other forces acting. Okay, if I'm pushing it, that doesn't count. It's not a projectile anymore. As I throw a ball, it becomes a projectile only after it leaves my hand, because that's the point where it's under the influence of only gravity. I can throw it straight up into the air. We'll call it a projectile. Or I can throw it at an angle. We'll still call it a projectile. Here's what I'd like you to do right now. I would like you to, just in the corner of your paper, or on scrap paper, doesn't matter, you're not handing this in. I would like you to draw a little picture. Here's a cliff. Here's the roadrunner running off the edge of this cliff. I want you to draw for me, please, just on scrap paper in the corner of your page, the path followed by this projectile, by the roadrunner, as he runs off the edge of the cliff. Okay? Give you 30 seconds to draw where you think this projectile is going to go, what the shape of the path is going to look like. How many people drew the shape of the path like you would see on TV, where the roadrunner goes off the edge, looks down, and then falls straight down? That's what happens in cartoons, right? Gravity doesn't actually act in cartoons until you look down. When you look down, that's when you start falling. Of course that's not right. Of course it's not going to go straight out and then look down and go straight down. Okay, that's not the right answer. How many people drew it something like this? Okay. That's closer, but that's still not right. You won't take a straight line path down. And the reason you won't take a straight line path down is because although gravity is acting down on you and will cause you to fall, there is no force acting horizontally. So if you've got no force acting horizontally and you do have a force acting vertically, you can't go in a perfect straight line. That doesn't work. The shape of the path is more like this. How many people had drawn something like that? Anybody know what the shape of that path is called? Laura might know what it's called. Yes? Yeah, go ahead. You're starting there. Laura, what's it called? A parabola, good. How many people have ever heard of a parabola? Just a few of you? Okay. Those of you who have heard the parabola, who have heard of a parabola, have you done the quadratic equation? Earlier we talked about Laura having just done the quadratic equation. Have some of the rest of you done it now? Yes? Okay. This is a parabola, and you'll see in a few minutes why it's a parabola and why one of the equations that we use to describe the motion of a projectile ends up being the equation for a parabola. An equation that we've already done ends up being the equation for a parabola. I want to show you something, though, real quickly here, a little demonstration. This goes back to the old, fire a bullet, how long does it take to fall, and drop a bullet, does it take the same amount of time to fall, and so on. If I fire a gun horizontally, just like this, pull the trigger at the exact same time, Travis, that I drop a bullet out of my hand straight down, which one's going to hit first? Which one's going to hit the ground first? We know that they're both going to hit the ground eventually, unless the bullet that I fire hits something, right? If it's got enough empty space, it will eventually fall and hit the ground. But which one's going to fall and hit the ground first? The one that I drop straight down or the one that I fire straight out? Yeah. Same time? Who says the same time? Who agrees with that? Yeah, that's not so intuitive. How many people think that the one that I fire from the gun is going to hit first? How many people think that the one that I drop straight down is going to hit first? That seems a little bit more intuitive, doesn't it? The one that you drop straight down is going to fall faster. It's going to hit the ground quicker than the one that's fired straight out. So we've got a few people agreeing with Rutger here. They're going to hit at the same time. And we've got most of the people thinking the one that we drop straight down is going to hit first. Here's a little demonstration I'm going to do. It's not involving a gun, by the way. Schools kind of shy away from using guns as demonstration tools in physics class these days. So we won't do that. Instead, we'll use this little projectile motion demonstrator thingy. It's got a little button on it, a little switch on it that if I push it, it releases a spring like that. Now what's going to happen is I'm going to put two little steel marbles, one on either end. The one that's on your left side is going to be left behind when the spring pulls this apparatus back. So in other words, it's going to fall straight down. Okay? It's going to be left behind, just like pulling the tablecloth out from underneath the dishes, right? The dishes get left behind. Okay? This ball is going to be left behind. It's going to fall straight down. But this one on your right side is going to be propelled forward by this little apparatus. They're both going to leave at exactly the same time, but one is going forward from a certain height, and one is dropping straight down from that same height. Okay, that's simulating at much lower speeds, of course, but still the same idea as firing the gun out and then dropping the bullet straight down. I want you to watch this, and I want you to listen. Okay, listening is sometimes easier to tell which one hits first, okay, by hearing the click as it hits the ground. Okay, watch closely, listen closely. Gonna push the button here. Again, the one furthest away from you right now is going to fall straight down. The one that's closest to you is going to be launched out this way. Nick, can I get you to stand over there, actually, just so that you can kind of catch it so it doesn't go underneath the table over there? It's not going to go far enough to actually hit you. So, okay, on the count of three, guys, we'll do it. 1, 2, 3. Didn't work. 1, 2, 3. Oops. That didn't work. Oh, I see. This thing is loose and it's kind of broken a little bit here. Okay, let's try this again here. All right, we got it fixed here now. Okay, we got one ball furthest away from you, one ball closest to you. We're going to push the button. One ball is going to drop. One ball is going to be propelled out. I want you to listen, and I want you to watch to see which one hits the ground first. Okay, 1, 2, 3. Which one hit first? Didn't catch it? Try one more time, okay? Okay, watch and listen. Watch and listen. I think if you see them both at the same time and listen carefully, I think the real answer is pretty clear when you actually see them properly. Okay, 1, 2, 3. Wayne? Which one hit first? Riker? They both hit at the same time. That's a little bit counterintuitive. The idea that the bullet that's fired straight out will hit at exactly the same time as the bullet that's dropped straight down. We would think intuitively that the bullet that's fired out by the gun at 300, 400, 500 meters per second, that bullet is going to take a lot longer to hit the ground than the bullet that's just dropped straight down. But it doesn't. And why doesn't it? Well, because in the end, there's only one force acting on both bullets, and that's the force of gravity. If there's only one force acting on both bullets, and that's the force of gravity acting straight down, then both bullets must be pulled downward at the same rate. The only difference between those two bullets, the one that's dropped straight down is going to hit right below where you dropped it. The one that's dropped, it's propelled outwards at 400 meters per second and falls at 9.81 meters per second squared, it's going to hit in the same amount of time, but it's just going to hit a couple kilometers away instead of just below where you dropped it. Does that make sense? Look, if you've only got one force acting and it's the same force acting on both of them, then they've got to fall at exactly the same rate and they've got to hit at exactly the same time. So the path that a projectile takes is called a parabola. And this is where we get into this little demonstration that we just did. The horizontal component of projectile motion, that's the x direction, right? The horizontal component, the x direction. It's constant velocity. In other words, there are no forces acting horizontally on this thing. This bullet that's fired horizontally, no forces acting on it horizontally. Therefore, it's not going to speed up or slow down horizontally. It'll travel at a constant velocity horizontally. Vertically, on the other hand, it's going to accelerate. Whether it falls straight down or whether it's propelled outward, it's going to accelerate downward at a rate of 9.81 meters per second squared. Now, to describe the x component, which is that constant velocity component, there's only one equation that we can use. It's a group A problem. We can use v is equal to delta d over delta t. When we're analyzing x, we've got to use that equation. When we're analyzing y, because it involves acceleration, we've got a whole bunch of options. We've got all of the group B equations. We've got A is equal to delta V over delta T. Vf squared is equal to Vi squared plus 2AD. Delta D is equal to Vi plus Vf over 2 times T. D is equal to VFT minus 1 FAT squared. And finally, D is equal to VIT plus 1/2 AT squared. They're all valid because for the y component, they all involve acceleration. Now, which one are we going to use most often? Which one seems to be the most useful to me? This one. So I want you to always start with this one. X component, use V equals D over T. Y component, let's use D is equal to VIT plus 1 FAT squared. Not because it's the only one we're allowed to use, but because it's the one that works the most often. How many people have ever been to head smashed in buffalo jump? It's kind of neat, eh? Head smashed in buffalo jumps. There's various buffalo jumps around. Head smashed in buffalo jump is not the only one in Western North America. These things, the English people, the British people here are going to have no idea what this is. Literally, a couple thousand years ago, even hundreds of years ago, natives in Western Canada and Western United States, they'd hunt buffalo, they'd hunt bison. And the way they often did it, it was kind of ingenious, actually. It's just incredibly simple the way they did it, but it was yet quite ingenious at the same time. They would herd these bison, hundreds of bison, into this kind of narrow column. Okay, basically chase them into this narrow column. Bisons, by the way, aren't known to be the smartest animals in the world. Okay? So they'd herd them into this narrow area, and they'd be running, and they'd be running towards the edge of this cliff. Bison aren't smart enough to stop when they get to the edge of the cliff, so they'd run right over. That's how they killed them all. Okay, we don't have to kill 100 bison with spears or with whatever, or with bows and arrows or whatever. We just have to run them off the edge of the cliff and collect them at the bottom of the cliff. So head smashed in buffalo jump is one of the best examples of places that we have, at least in Western Canada, of what these natives used to do literally running these bison off the edge of this cliff. They'd be running up here, oops, they'd fall off the edge of the cliff. They'd die when they hit the bottom there, and then they'd collect them and get their pelts and get their meat and whatever. Hedgemaster Buffalo Jump is near Fort McCut. It's only a couple hours away if you want to go see it. It's a UNESCO World Heritage Site. Over 6,000 years ago, the Blackfoot people of the plains hunted North American bison by gathering herds and directing them over cliffs 20 meters tall. Assuming the plain was flat so that the bison ran horizontally off the edge of the cliff, and the bison were moving at their maximum speed of 18 meters per second. That's pretty fast. For such a fast animal, it's too bad they weren't a little smarter. Okay? We want to know how far from the edge of the cliff that these bison are going to land. What do we do? Well, the first thing we're going to do is draw a picture. Let's draw a picture of the cliff, a simplified picture of the cliff. Okay, there's the cliff. Then we've got we'll just draw one bison. He's smiling because he has no idea what's coming. Doesn't know that he's about to run off the edge of the cliff. Hey, this is fun. Saying, it's been a while since I've ran with 100 of my best friends. This is fun. Got to put a tail on him here. Do bisons have tails? I don't know. They must. Right? They must. Let's put a little. Let's put a little blue tip on the end of his tail. This is the lesser-known variety of bison called the blue-tailed bison. You guys ever heard of blue-tailed bison? Okay. They were around about 6,000 years ago. Okay, they went extinct because they all ran off a cliff in Fort McLeod. Anyways, here we've got this blue-tailed bison that's running at 18 meters per second off the edge of the cliff. We know the path that this bison takes is a parabola, so it's going to look something like this. We know the height of the cliff is 20.0 meters high. And we know that the bison is going to end up over here somewhere. We just don't know how far from the edge of the cliff that he's going to land. That's, in fact, what we want to find. How far from the edge of the cliff, the base of the cliff, that it's going to land. For the last week or more, we've been dealing with two-dimensional problems, and this is no different in that respect. This is a two-dimensional problem as well, because there is a component of this bison's path that is horizontal, constant velocity horizontal, and acceleration vertical. So we have to break it up into those two components, the x component and the y component. The x component will always be described by this equation. Every single time. When I give you a question on the test, on your test next week on this, can I ask you to analyze the motion of a bison or the motion of a ball or whatever, and you break it up into x and y components, you need to put v equals d over t for the x component. I don't care what the question says, v equals d over t is going to be what you write down for the x component. Now, for the y component, there's a number of options, a number of equations that we're allowed to use, any of the group B equations. But the one that we're going to choose is this one, because it's the one that works the most often. Even though it's not the only one that's valid, it works the most often. All right. Notice I haven't really given you a strategy yet. I've told you, here's the equations that are valid, but I haven't really told you how to solve it. It's really because there is no strategy. It's just plug in your numbers. Plug in whatever numbers you have and find something. Okay, it's probably not going to be what you're looking for right away. That's okay. Just get something, and then get what you're looking for later on. Do we know the x component of the velocity here? Do we know how fast this bison is running on the x-axis? Aiden? 18 meters per second. Okay, the bison is not running up into the air at 18. The bison is not running up into the air at an angle. So none of it's up into the air. All of it is horizontal. All of it is on the x-axis. So we're going to plug in that value 18 meters per second here. The horizontal displacement, I don't know. But in fact, that's what I'm actually trying to find here, right? How far the bison goes horizontally before it hits the ground. The time, I also don't know. So that didn't seem overly helpful to me, actually. That's okay. I plugged my numbers in because I could. Remember, the strategy is just plug numbers in, see what happens. That didn't work out for me, so let's go to the y component now. Do we know what the y displacement is of this bison? This little-known blue-tailed bison? Hayden? Almost. It's negative 20 meters because it ends up 20 meters below where it started. So let's plug in negative 20 for the displacement. Horizontal displacement, we didn't know what that was because we don't know how far from the edge of the cliff that it lands, but we do know how far it falls. Falls 20 meters. What's VI for the y component? Clearly, as this bison falls, it's going to speed up vertically, right? But how fast is it moving vertically when it leaves the edge of the cliff, Riker? 0, yeah. It's moving at 18, but it's all horizontal. None of it's vertical. So we can cross this term off. 0 times whatever the time is 0. Vertically, the acceleration is negative 9.81 times t squared. Now we only have one unknown. Now we can solve for t here. Let's pull out our calculator and do this as a group here. Let's say neg 20. We can divide neg 20 by a half. Neg 20 divided by 0.5. We can also divide it by neg 9.81. Okay, 1/2 and 9.81 are both multiplied by t squared. So let's divide by a half. Let's divide by neg 9.81. Gives me a value of 4.077. But that's not t. That's t squared. How do I get t from that? Hayden? The square root it, right? 2.0193. So we don't know how far from the base of the cliff that the bison lands, but we do know how long it takes the bison to fall. 2.0193 seconds. What are we going to do with that? Hayden? Plug it into the x. Why can I do that? Hey, how come I can go from x to y like that and y to x? Why am I allowed to use the time in both x and y, but I'm not allowed to use a displacement in both x and y? It's two different values here. Good. Time is a scalar, displacement is a vector. Okay? Displacement has to go with either x or y. Time can go with both. Let's plug in the value of time now. 18 equals delta d over 2.0193. The 2.0193 goes up by multiplying. Multiply it by 18, and I get a value of 36.34. How far does the bison fall? 20 meters. How long does it take him to fall? 2.01 seconds. How far does he land from the base of the cliff? 36.3 meters. Reggie? As he was falling? No. No, absolutely not. The bison, in fact, would speed up as he's falling because gravity is acting. Technically, yes, a small amount because of air resistance. But in all of the problems that we'll do with projectile motion, we will approximate air resistance to be 0. I had a professor in university years ago. He defined physics as the art of making the right approximation, which I kind of like that definition, actually, because nothing's ever perfect. Nothing that we do is ever perfect. There's always an approximation. As long as we make a good approximation, then we're doing pretty good physics. Okay? This bison is running at 18 meters per second. He's heavy. Okay, the air resistance acting on this bison is very, very small. He's not going to slow down very much at all. Okay, so we're going to assume that he's just traveling at a constant velocity. Now, not all things are the same. If I take a piece of paper and ball it up and throw it, well, then air resistance is going to be a lot more significant on that piece of paper, right? So that's not such a good approximation. In all the problems that we do, okay, we'll assume that horizontally there's no air resistance acting, so it's not going to slow down. Okay, we'll assume that it's more like the bison where the mass is enough that there's just not very much air resistance there. Okay, it's a good question. Does that make sense? Okay, you know what's next, right? You're going to get a couple of questions on this same thing. When you do those questions at your desk, I want you to do the exact same thing we've done up on the board here. Draw the picture. Break it into X and Y. Write down the equations. Don't take shortcuts here, okay? You want to do this right? Then write everything down. Take the time and do it right. Okay, if you have questions, put up your hand and ask them. Let's try questions 1, 2, and 3, actually, on page 107. All right, number 1 says a coin rolls off the edge of a table with an initial horizontal speed of 30 centimeters per second. I'm going to just circle that centimeters to remind me to convert that to meters per second in a minute. How far will the coin land from the base of the table if the table's height is 1.25 meters? We should draw a picture for this. Okay, here's my picture. Looks a lot like my blue-tailed bison running off the edge of a cliff, except this time I got a coin rolling off the edge of the cliff. The coin is initially rolling at 0.30 meters per second, 30 centimeters per second, or 0.30 meters per second. And it goes down a height of 1.25 meters, the height of the cliff. The shape of the path is called a parabola. What am I looking for here? How far from the base of the table is it going to land? I'm looking for delta D x component. Now, let's break this up into x's and y's. The x component will always be described by the same equation every single time. Okay, there is no excuse, there's no reason in the world why we can't all write down that equation for the x component, because it's always the same. We don't have to be smart. Okay, we don't have to have a good memory. We just have to remember the simplest equation that we've done this year is always the one that goes with the x component in projectile motion. No exceptions. Now for the y component, it's a little bit trickier because there's 5 options that we have. All of the group B equations apply here. The one that we're going to use, though, or the one that we're going to try at least, is the one that is usually the most useful, the one that works the most often, VIT plus 1 FAT squared. Write that down first. Okay, you don't have to know for sure which equation we're going to use for the y component. You just have to write down the one that's probably the one that's going to work. And if it doesn't work, try something else. All right, let's plug in some values here now. The x component of the velocity is 0.30 meters per second. All of it is horizontal. None of it's vertical. None of it's up and down. The displacement, we don't know that. That's what we're looking for. The time, we also don't know. So it's our second problem in a row now where we've gone to solve the x component, but we haven't really gotten anything out of it. So what do? We don't get anything out of it, we go to the y component. Let's start plugging in values for that. The y displacement is negative 1.25 meters. Negative because it's down. 1.25 because so far the coin falls. What's the value of VI? Aiden, what's the value of VI there for the y component? Good. Why is it 0? Okay, it's not 0 because it falls. It's 0 because when it leaves the edge of the table, it's not falling. Right? V changes. V starts off as 0 on the y component, but it becomes bigger values as it goes down and speeds up. But initially, when it's rolling off the edge of the table like this, okay, here's my coin. Okay, how fast is that coin moving up or down? Not at all. It's moving only horizontally. So VI for the y component in these problems will be 0. It's equal to 1/2 of negative 9.81 times t squared. Now, let's do that on our calculator as well. Let's say negative 1.75. Let's divide that by 0.5. That's a half, right? Let's also divide it by neg 9.81. So we're dividing 1.25 by a half and by negative 9.81. We get a value of 0.3567. Let's square root that. We end up getting 0.5973. So the time that it takes this coin to fall is 0.5973 seconds. 1.25, wasn't it? Did I put 1.75? Yes, I did. Thank you. So that number is going to be different there because I plugged the wrong number in. Negative 1.25 divided by 0.5 divided by neg 9.81. What did I divide it? The half is multiplied by t squared. So is the 9.81 multiplied by t squared. How do I get them both over? I divide them both. Let's square root that. 0.5048. So not hugely different, but a little bit different. Thank you, Rutger. Say it again. Yeah, kind of all in one step there. Yeah, that's fine. Just be careful with brackets on your calculator there. The alternative to that, Travis, is to actually calculate this value first. A half times 9.81 is 4.905. Then you could say 1.25 divided by 4.905. That would work just fine. Yeah. So my time is 0.5048 seconds. We now have 0.30 meters per second is equal to the horizontal displacement over 0.5048, which we're going to take up by multiplying 0.5048 times 0.3 gives me a horizontal displacement of 0.151. What's the answer? What's the answer of the book? It says 15 centimeters. What did I get? 0.15 meters. Is that the same thing? Yeah. Yeah, it's the same thing. So I don't care whether you put it in centimeters or meters on a test. Both would be marked correct, obviously. Yep. Yeah, now be careful with that. Be really, really careful with that. In this question, you'd get away with it. But I don't want you to make that habit, be in that habit, because you won't always get away with it. Okay, the question was, for those of you who didn't hear, basically, do we have to convert centimeters per second to meters per second? In this question, we would get away without converting. Okay? But if VI was not 0, if VI for the y component was a certain value other than 0, then that wouldn't have worked out for you. Okay, so my strong suggestion is just always convert, because it always works to convert to meters per second. Occasionally it works if you don't convert, but it always works if you do convert. I'd rather go with always than occasionally. Okay? I wouldn't mark it wrong. Yeah, I wouldn't mark it wrong, but just be aware that it's not going to work all the time. All right, we'll give you a little bit more time to work on questions 2 and 3 here now. I'm going to point out something for question 2, though, so that you're not kind of let off on a wild goose chase on this. This 150-meter tall cliff is irrelevant. Can anybody explain to me why the 150-meter high cliff means nothing in this question? Yep. Yeah, we're told that it falls for 2.5 seconds. We don't know if it falls to the bottom of the cliff or not. Maybe it falls 150 meters, maybe it falls 75 meters. We don't know. We're told how high the cliff is, but that doesn't say anything about the motion of the arrow. So we don't know what the y displacement is in question number 2. We want to know how far it falls. We want to find the y displacement. Okay, does that make sense? Don't get mixed up with that, okay? You want to use data for the motion of the object. And 150 doesn't describe the motion of the object at all. It describes the cliff. And that's not what we're studying here. Okay, so try 2 and 3. Put up your hand if you have some questions.